Today I'll be talking about Phase 2 testing for a treatment effect in marker-defined subsets, and in particular about using the group sequential testing machinery to carry out this testing. So here is an outline for the talk. First we'll delve into what we're trying to learn from the testing of marker-defined subsets. This material is drawn somewhat from the book Theory of Drug Development. Then we will turn to using spending functions to control the type 1 error from testing for a treatment effect in multiple marker-defined subsets. And finally, we will look at the results of a simulation that compare the results of this spending function procedure with some other benchmark approaches to testing marker-defined subsets. And finally, I should note that in this talk, we assume that the clinical setting is an oncology trial with PFS as a primary endpoint, and a comparison between treatment and control is made with the log rank test. Okay, so we will start with the objective of testing in Phase 2. When thinking about how to set up the test for marker-defined subsets, two basic objectives or approaches come to mind. One approach is to simply test for a treatment effect in each marker-defined subset. That is, in each marker-defined subset, we compare PFS in the treatment group with PFS in the control using the log rank test. An alternative approach is to compare the treatment effect on PFS in each marker-defined subset with the treatment effect in the complement of this subset to see if there is a difference. That is, to see if the Phase 3 trial could be enhanced by excluding subjects from the complement of this marker-defined subset. This second alternative would seem to be the preferred approach, except for the fact that it is a harder question to answer. To answer the question of whether the treatment effect in a subset is greater than the treatment effect in the complement requires comparing PFS in 4 groups, since we're comparing treatment and control in the marker-defined subset and treatment and control subjects in the complement of the marker-defined subset. On the other hand, answering the question of whether there is a treatment effect in a subset requires comparing only 2 groups of subjects, treatment and control subjects in the marker-defined subset. In essence, when we are detecting a treatment effect, we have 2 sigma squared in our denominator for the log rank test, while when we are looking for the best subset to study, we have 4 sigma squared in the denominator of the z-statistic for the log rank test. So, what should be the objective of testing marker-defined subgroups in Phase 2? The answer to this question, I would argue, depends on the drug development setting. Drug development is carried out primarily by drug companies, which are economic entities trying to maximize profits. If we assume that a drug company attempts to maximize the probability that the drug development of an effective drug will end with a successful Phase 3 trial, all this subject to a constraint on the resources utilized, then it can be shown that the drug company will attempt to maximize the efficiency of drug development, which is defined here on the first line of the slide. Efficiency is the ratio of the probability of a positive Phase 3 for an efficacious drug divided by the expected cost of development. It's assumed here that Phase 3 is undertaken only when the Phase 2 trial is positive. Efficiency is further detailed in the second line of the slide. The numerator of efficiency is the prior probability that the drug is effective times the power of the Phase 2 trial times the power of the Phase 3 trial. The denominator is the present value of the pre-Phase 2 development costs plus the expected sample size in Phase 2 and Phase 3. Now we can factor out the efficiency of a Phase 3 trial alone, that is, a Phase 3 trial without a preceding Phase 2, as we have here in the second line of the slide. And what we have remaining is the factor by which efficiency changes because of the Phase 2 trial. We call this factor the relative efficiency of the Phase 2 trial. It is the power for Phase 2 divided by the ratio of the expected total costs when a Phase 2 trial is conducted relative to when a Phase 2 is not conducted prior to Phase 3. Here in this slide is an example of how the relative efficiency behaves as a function of the treatment effect size. Each panel represents a different level of pre-Phase 2 development costs. The left panel, where C equals 0, corresponds to the situation where there are no pre-Phase 2 drug development costs, as in the case where a second indication for a drug is under investigation after receiving initial approval. The right panel, where C equals 1, corresponds to the situation where a drug company has discovered a molecule in their research labs, and the present value of costs incurred prior to starting phase 2 are about equal to the costs of undertaking phase 3. This situation is very common for a new molecule. The scale for the treatment effect on the x-axis is the proportion of the treatment effect size that would be used to power the phase 3 trial. We can see that in the first panel, where there are no pre-phase 2 drug development costs, a phase 2 trial may improve the efficiency of drug development by 30% when the treatment effect matches what would be used to plan phase 3. On the other hand, when there are pre-phase 2 development costs that are the same as the phase 3 costs, the situation described in the third panel, the efficiency of development is reduced by a phase 2 trial that's used as a screen to determine which molecules are studied in phase 3. So basically, when the pre-phase 2 development costs are large, it's not wise to stop development based on an underpowered phase 2 trial, which will provide unreliable results. But are there other reasons to conduct a phase 2 trial? Well, the answer is yes. Phase 2 can be used to optimize phase 3 by choosing the appropriate dose or the appropriate subset of subjects to study in phase 3. The expression in this slide presents the relative efficiency of a phase 2 trial that's used only to select a subgroup to study in phase 3. There's no screening for whether to study the molecule in phase 3 here. The numerator is the probability that the phase 3 trial is positive when we study the best looking subset in phase 2. The denominator is the probability that the phase 3 trial is positive when the subset that is studied is selected at random. Okay, so here we plot out the efficiency of a phase 2 trial that selects the proper subset to study in phase 3. This graph shows that the efficiency of drug development can be improved 30% in the case where one of the marker subsets has no activity while the other has a treatment effect of the same size as that which would be used in planning for phase 3. And we see a similar pattern here with larger and smaller treatment effect sizes, as is displayed in the figure. Okay, so in a large pharmaceutical company that has considerable resources invested in a molecule, the phase 2 trial shouldn't be used as a screen to determine which drugs to study in phase 3. Instead, phase 2 should be used to identify where the treatment effect may be the most promising. For example, the dose that would be the best, or the marker subgroup. This is a setting where the objective in phase 2 should be to determine the best marker subset to study in phase 3. Alright, now some of you may be thinking, well, why shouldn't phase 2 be used to rank which molecules look more promising and should be studied in phase 3? So let me say a little more about this. If a drug company is in a situation where there is not enough money to pay for a phase 3 trial for all molecules that have completed phase 2, then of course you would have to pick which ones will be studied in phase 3 based on the phase 2 results. The point here is that a drug company that finds itself in this situation is a poorly run company. That it would be much more efficient if its resources were allocated so that there was enough money to study in phase 3 all the molecules that completed phase 2 without appearing to harm patients. And this is because phase 2 trials are underpowered, and the chances of making a wrong decision are quite high, and the resulting waste of money is quite large for a new molecule. So assuming that a drug company has properly allocated its resources, phase 2 should not be used to screen which new molecules to study in phase 3. Okay, a large pharmaceutical company looking for a second or third indication for an improved molecule will benefit from using phase 2 as a screen for activity. And that's because the pre-phase 2 costs are already covered. In this setting, the primary objective in phase 2 should be screening for activity to determine whether phase 3 should be undertaken. Okay, a small biotech company that receives milestone payments at the end of phase 2, if a pharmaceutical company opts in on the development of a molecule, wants to develop evidence that the drug has activity. In this setting, screening for activity in phase 2 should be the primary objective. Okay, now it's interesting to note in this situation that the interests of the pharmaceutical company and the small biotech company would diverge from a pure drug development perspective. A small biotech would have a large investment in the new molecule, and so would want to use the phase 2 trial to optimize the phase 3 design. The large pharmaceutical company, on the other hand, without such an investment, would be more interested in using phase 2 as a screen for an active molecule. So collaborations between small biotechs and large pharmaceutical companies could lead to suboptimal drug development. It's a suboptimal development that small companies are willing to tolerate, however, because they receive considerable financial resources if the large pharmaceutical company decides to develop the drug. To sum up, whether the primary objective in phase 2 is to screen for active drugs, which will be studied in phase 3, or to identify the best subset to study in phase 3, depends on the investment in the molecule at the time of initiating phase 2. Situations where the pre-phase 2 investment is large should lead to phase 2 trials whose objective is to find the best subset to study in phase 2, while situations where the pre-phase 2 investment is small should lead to phase 2 trials whose objective is to act as a screen to determine which drugs will be studied in phase 3. The spending function approach for testing marker-defined subsets presented here, and which will be discussed next, is intended to be used primarily when screening for drugs to be studied in phase 3. Okay, so now we'll turn to using spending functions to control a type 1 error from testing for a treatment effect in multiple marker-defined subsets. Before we get started, I should say a little about how I'm using the terms 25, 50, and 75th percentile. This slide defines how I'm using percentiles to define groups of subjects. A group of subjects with marker expression greater than the 75th percentile has high marker expression, while the group of subjects with marker expression less than the 25th percentile has low marker expression. I'll use the phrase subjects with marker expression greater than the 25th percentile sometimes. That refers to the 75% of the study population with the highest marker expression. Okay, so let's set some notation. We'll use lambda 1 through lambda 4 to define a treatment effect in each of 4 marker subsets, which are defined in terms of the quartiles of the marker distribution. Lambda 1 represents the treatment effect in subjects with marker expression greater than the 75th percentile. Lambda 2 represents the treatment effect in subjects with marker expression between the 50th and 75th percentiles. Lambda 3, the treatment effect between the 25th and 50th marker percentiles, and lambda 4, the treatment effect in subjects with marker expression less than the 25th percentile. The hypotheses that we're interested in testing are listed here. As you can see, they involve testing overlapping marker subsets. That is, we test for a treatment effect, hazard ratio less than 1, in subjects with marker expression greater than the 75th, 50th, and 25th percentiles, as well as in all subjects enrolled in the study. Now, if we wanted to reconstruct a series of interim analyses after a study has completed, we would order subjects by the calendar time at which they entered the study. Subjects whose calendar time of study entry fell before the calendar time of the first interim would be included in the first interim analysis. Subjects whose calendar entry time fell before the second interim would be included in the second interim analysis, etc. Okay, so how can we apply the group sequential framework to the evaluation of marker-defined subsets? Well, instead of ordering subjects by the time they enter the study, we can order them by their marker expression. Those with marker expression less than the first cutoff are included in the first analysis. Those with marker expression less than the second cutoff are included in the second analysis, etc. Thereby, we can use the machinery developed for group sequential analysis to control type 1 error and calculate power. This slide describes the basic calculations for group sequential error probabilities in terms of the z-statistic for the mean of normally distributed data. Let z1 and z2 be the simple z-statistics for samples of sizes n1 and n2 in the treatment and control arms. Here we take n2 to be greater than n1. That is, the second z-statistic summarizes all the data in the study at a later time than the first z-statistic. Then we can write the conditional probability that Z2 is greater than Z alpha, given Z1, as we have here in the middle portion of the slide. And the probability that Z2 is greater than Z alpha is then just the integral of this probability with respect to Z1, which we have in the last line of the slide. We can see now that all that's required for these calculations to hold is the definition of the two overlapping groups of subjects. With interim analysis, we define the overlapping groups with respect to time, and what we are presenting here, we define the overlapping groups in terms of marker expression. And the equations for calculating the probabilities are exactly the same in both cases. So there's nothing earth-shattering here, just a simple rephrasing of interim analyses so that the theory can be applied to the problem testing hypotheses on marker-defined subsets. Next, we'll provide an example of this sort of testing procedure. In the example, we use the gamma family of spending functions with the parameter gamma set equal to -1. The slide here presents a graph of the spending function when gamma equals -1, as well as the equation that describes the gamma family of spending functions. I should note that any spending function could have been used here. Of course, different spending functions will give the testing procedure different properties. Okay, so this slide presents the rejection boundary for the test of H4, the global null hypothesis, based on the gamma -1 spending function, along with the type 1 error and the power for various alternatives. The first two rows of the table present the critical value for the z-statistic that's used for each marker subset and the associated number of events in each marker subset. In practice, this z-critical value may have to be recalculated once the number of events in the marker subset are determined. There are 106 events planned for in the trial. The z-critical value starts out at 2.13 for the first test of subjects with biomarker expression greater than the 75th percentile and decreases to 1.45 for the test in all subjects. The third row of the table presents the type 1 error for the procedure. In this case, starting out at 0.016 for the test of subjects with biomarker expression greater than the 75th percentile, and increasing to 0.1 overall for the cumulative type 1 error across the test for all 4 marker subsets. The remaining rows of the table present the power under various assumptions about the hazard ratios in the marker subsets. Note that our alternatives are of the form, for example, lambda 1 equals lambda 2 equals 0.75. That is, the alternatives have a constant hazard ratio across the subsets being examined for power. This is because we are using a formula for calculating the power that requires constant hazard ratio. Power calculations for non-constant hazard ratio alternatives require simulation. Okay, so the test will have 80% power to detect a hazard ratio of 0.65 in the study population as a whole. There is 75% power to detect a hazard ratio of 0.5 in subjects with biomarker expression greater than the 50th percentile. There is 75% power to detect a hazard ratio of 0.335 in the subset of subjects with greater than 75th percentile marker expression. The low power in this subset is partly a consequence of keeping the power at 75% for the whole study population with 105 events and a hazard ratio of 0.67. It's also a consequence of the small number of subjects in the subset. Only large treatment effects can be detected in this group with such few events. A spending function along the lines of the Pocock boundary could just as easily be used here instead, and it would have resulted in a bit more power for this subset. Now, it's interesting to note that if we consider the set of hypotheses H1 through H4 as elemental hypotheses, then it turns out that the set H1 through H4 is a closed set. The intersection of any two hypotheses in the set is also in the set. And so family-wise type 1 error control can be achieved if we test in the order H4, H3, H2, H1, and stop testing as soon as we fail to reject a hypothesis. So if we suppose that H4 is rejected, what does the test of H3 look like? Okay, so here on this slide we have a test for H3 constructed similarly to how H4 was constructed. except that we are testing 3 hypotheses instead of 4. That is, we are testing for a treatment effect in subjects with marker expression greater than the 25th, 50th, and 75th percentiles. This test for H3 has lower Z critical values than the test for H4 since there are fewer tests to allocate alpha over. For example, the critical value for the biomarker subset with expression greater than the 75th percentile is 1.99, as compared with 2.33 in the test for H4. If H3 rejects, then we can continue on to test H2 while maintaining family-wise control of the type 1 error. Here, H2 is constructed just as H4 and H3, except now there are only 2 marker subgroups to test. Once again, the critical value for the biomarker subset with expression greater than the 75th percentile has dropped to 1.77 from 2.13 in the test for H4 and 1.99 in the test for H3. The power to detect a hazard ratio of 0.335 is now 85%. And finally, if H4, H3, and H2 are all rejected, then we can test H1. Our last test for whether there is a treatment effect in subjects with marker expression greater than the 75th percentile has a critical value of 1.28, and the power to detect a hazard ratio of 0.335 is 94%. At this point, there will be adequate power for detecting more reasonable hazard ratios, but it is still dependent on rejecting the previous 3 tests for H4, H3, and H2. One may wonder what is the point of doing all this testing. Why not just perform the test for H4 on the whole study population and stop? The answer is the additional testing gives us greater power to detect a treatment effect in the marker subsets compared to just performing the test for H4. It is true that the power for detecting any sort of treatment effect does not change by doing this additional testing, since it depends solely on the power for the first test, the test for H4. Okay, so what can we formally conclude when we are done with this testing? Well, we can conclude that the experimental agent prolongs progression-free survival for some markers-defined subset of the subjects studied, if not all subjects. And this answers the drug development question, does the drug have activity? But let's investigate what we can conclude a little further. Suppose that in our testing, H4, H3, and H2 are rejected. Then we can formally conclude that there is a treatment benefit among subjects with marker expression greater than the 50th percentile. This is because H2 and all the interaction hypotheses containing H2 are rejected. However, we can say the same thing for H3 and H4, that there is a treatment effect in subjects greater than the 25th percentile in marker expression and in all subjects. So the results do not allow us to formally conclude that the treatment effect in subjects with marker expression greater than the 50th percentile is greater than the treatment effect in subjects with marker expression less than the 50th percentile. Now, some of you may be thinking, well, why not first test for a treatment effect in subjects with the highest marker expression? And the reason is this would miss a moderate treatment effect in all subjects if there is not also a large treatment effect in those subjects with high marker expression. And further, testing in all subjects first as proposed here would allow one to detect a moderate treatment effect in all subjects while still being able to detect a large treatment effect in subjects with high marker expression if there is one. Okay, so although we are considering the situation where the primary objective of Phase 2 is to detect a treatment effect, the question, what is the best subset to study in Phase 3, still has to be answered at some point. This question could be addressed in the same Phase 2 trial, although this is likely to be very underpowered. It could be addressed by looking at other Phase 2 trials, perhaps in other indications, by looking at more data in a follow-up Phase 2 trial, or by explicitly incorporating the determination of the answer to this question directly into the design of the follow-up Phase 3 trial. One could consider using the adaptive population enrichment design proposed by Cyrus Mehta along with Schaefer, Daniel, and Erlisle in their 2013 Statistics of Medicine paper. Alternatively, one could consider using the biomarker adaptive threshold design proposed by Jiang, Fridlin, and Simon in 2007. Now let's look at the results of a simulation that compared the results of this spending function procedure with some other benchmark approaches to testing marker-defined subsets. Okay, so 3 benchmark tests are included in the simulation, in addition to the spending function approach discussed here today. An overall test for treatment effect, a marker by treatment interaction test in the Cox model, and a test based on the Holm or Hochberg procedure. The alternatives used here to evaluate the power have hazard ratios ranging from 0.335 to 0.8. Constant hazard ratios as well as non-constant hazard ratios across the marker subsets were used. For non-constant hazard ratios across the marker subsets, the hazard ratio was only allowed to increase in the direction of a hazard ratio of 1, a no effect hazard ratio, as the marker expression decreased. This slide presents a graphical summary of the simulation results. For a wide variety of situations, powers for the spending function approach represented on the x-axis are compared with powers from the test for an overall treatment effect, the test for an interaction, and the test based on the Holm-Hochberg procedure. These 3 tests being represented on the y-axis. We can see that for the most part, the plot of the paired powers lie below the 45-degree line, which indicates that the spending function approach generally has more power. In this slide, the powers for the group sequential approach are represented once again on the x-axis, while the powers for the test aimed at detecting a difference in the treatment effect between subjects in a marker-defined subset and its complement are presented on the y-axis. The graphs in the first 3 panels, labeled L1 through L3, concern interaction tests, where the population is split at the 25, 50, and 75th percentiles. The test in the last panel, labeled I-Holm, is a combination of these 3 tests, where the type 1 error is controlled with the Holm procedure. To start, we can see that when the Holm procedure is used to control a type 1 error from these 3 tests, the power is less than for the group sequential approach developed here, thus highlighting the advantage of using the group sequential approach to answer the drug development question: does the drug have activity that's worth studying in Phase 3? Now, if we look closely at the figure in the last panel, we see that there are a few instances where the power of the Holm interaction test has the same power as the group sequential approach. We can see from the first panel on the figure that the power for the interaction test slightly exceeds the power for the group sequential approach in a few instances where the treatment effect is restricted to the subjects with marker expression greater than the 75th percentile. This may be due in part to the fact that the gamma-1 spending function allocates the least amount of type 1 error to the assessment of a treatment effect in this group, while the power for the interaction test is evaluated with respect to 0.10 type 1 error. Okay, so to evaluate how well the spending function testing procedure identifies the best subset to study in Phase 3, we take a look at the power for the following alternatives. These alternatives represent treatment effects restricted to subjects with marker expression greater than the 25, 50, and 75th percentiles. Okay, so here we have a table that presents a subset of the simulation results discussed previously. In the case where the hazard ratio is 0.5 for subjects with marker expression greater than the 50th percentile and 1 for subjects with marker expression less than the 50th percentile, the row that is bold-faced on the slide, we see that the power to reject the null is 0.733 when testing lambda 1 equals 1 or lambda 2 equals 1. that is when testing in subjects with marker expression greater than 50th percentile. The additional power gained by testing in the subsets where there is no treatment effect is only 8% in this scenario. So in this case, the spending function approach seems to do a reasonable job of identifying the appropriate subset to study. On the other hand, the slide also shows that when there is low power, as when the hazard ratio is 0.670, a considerable portion of the overall power is made up of false positives from testing in subjects greater than the 25th percentile or testing in all subjects. Finally, note that when there's a large treatment effect, that is a hazard ratio of 0.335, for example, across all the marker subsets, H1 and H2 have a good chance of being rejected even though the treatment effect applies to all marker subsets. So this table shows that the group sequential testing approach presented here has to be supplemented with other tests and preferably additional data to determine the best subset to study in Phase 3. That's the end of my talk. Thank you very much.